This next video is about the acceleration of the universe. This is a very recent discovery from the past 20 years or so, and it actually won a Nobel Prize in 2011, which we will discuss later in the video. Now, in the last video, we plotted up the velocity of a bunch of faraway galaxies, or somewhat faraway galaxies, as a function of their distance. And we found that the further away the galaxies are away from us, the faster they are moving. And we discussed how this was credited to Hubble, though probably that was a little too much credit, because other people, primarily Vesto Slipher, have measured the velocities of the galaxies. That the theory behind it was thought up by George Lemaitre, and he's considered kind of the father of the Big Bang theory. And this straight line has to do with what's called the Hubble constant, which is also related to the Hubble time, which is how long ago these things were in the same place at the same time, when everybody was here. These were data from the astronomical literature, and these distances were found many different ways. So the error bars here you can see are quite small. They're smaller than these here, but you can still start seeing a little bit of the error in the distance. There have been a number of surveys in the early 21st century using supernovas as the standard candle to find the distance. And they make a plot like this out to much further away galaxies. This is the topic of this next video. This here is the same plot as we just showed, but at a completely different scale. You see how this goes all the way up to 6,000 megaparsecs, which, if we recall from our last video, is actually larger than the size of the whole universe as we already calculated it to be from before. Now, this dashed line here represents the best fit Hubble's law that we had calculated from before using the other data and also various other measurements that are independent that astronomers use. Notice the velocity axis goes all the way from 0 to 300,000 kilometers per second. And recall that that was the speed of light from the last video. So over here I've plotted another axis with the velocity as a percentage of the speed of light. So the very top would be the speed of light, very bottom is 0, and then on this axis here is the distance in megaparsecs, just like before. So remember we found that the age of the universe was 14 billion years. That's why we have a 14 here. On the top axis, I've plotted something called the look-back time. And the look-back time is how long ago the light left the galaxy. So the further away a galaxy is, the bigger the look-back time. So you can see that if you follow Hubble's law all the way up, that we cross this axis here at a point that's a distance that corresponds to 14 billion light years. In other words, it would take light 14 billion years to travel from the beginning of the universe to the edge. That's how we got the age of the universe, and we called that the Hubble time. So now, here's the catch. As you can see, when we have lots and lots of galaxies that are relatively close by to us, we have this beautiful representation that follows Hubble's law just like our last video. However, you can see, if you kind of notice this, there's a trend kind of like this in the data. So you can see that for a given distance a galaxy is away, it's not moving as fast as we might have expected from Hubble's law, which is kind of an odd thought. Therefore, maybe some of our assumptions having to do with Hubble's law are actually not so. For example, one of our assumptions was that all of the galaxies move at a constant velocity since the beginning. In other words, the universe as a whole is expanding at a constant rate. Well, clearly, maybe that's not true. Maybe we have maybe this curve here has to do with some sort of acceleration of the universe. Either it's speeding up or it's slowing down over time. Much like if you're driving your car down the road at a constant speed, you're not accelerating. But if you hit the gas, you accelerate forward, you hit the brake, you accelerate backwards. So one of our questions is going to be, is the universe speeding up over time, or is the universe slowing down over time? Our first thought would be that it probably would make sense for it to be slowing down over time, because the gravity of all the rest of the universe would be pulling on it. So we're going to see if that actually is the case based on the data we have here. So first thing I'm going to do is read the caption for you all so you all know what we're plotting. Each point on this plot represents a galaxy where a type 1 supernova has been observed. On the y-axis apply the velocity of the galaxy, and on the x-axis represents the distance to the galaxy. Notice the error bars. The dashed straight line represents Hubble's law with Hubble time of 14 billion years, or h0 equals 68.5 kilometers per second per megaparsec. And the red thick line represents the best fit quadratic curve of these data. There have been a number of surveys in the early 21st century using supernovas as the standard candle to find the distance. And they make a plot like this out to much further away galaxies. This is the topic of this next video. This here is the same plot as we just showed, but at a completely different scale. You see how this goes all the way up to 6,000 megaparsecs? We recall from our last video is actually larger than the size of the whole universe as we already calculated it to be from before. Now, this dashed line here represents the best fit Hubble's law that we had calculated from before. The velocity axis goes all the way from 0 to 300,000 kilometers per second. And recall that that was the speed of light from the last video. So over here I've plotted another axis with the velocity as a percentage of the speed of light. So the very top would be the speed of light, very bottom is 0, and then on this axis here is the distance in megaparsecs, just like before. So remember we found that the age of the universe was 14 billion years? That's why we have a 14 here. On the top axis, I've plotted something called the look-back time. And the look-back time is how long ago the light left the galaxy. So the further away a galaxy is, the bigger the look-back time. So you can see that if you follow Hubble's law all the way up, that we cross this axis here at a point that's a distance that corresponds to 14 billion light years. In other words, it would take light 14 billion years to travel from the beginning of the universe to the edge. That's how we got the age of the universe, and we called that the Hubble time. So now, here's the catch. As you can see, when we have lots and lots of galaxies that are relatively close by to us, we have this beautiful representation that follows Hubble's law, just like our last video. However, you can see, if you kind of notice this, there's a trend kind of like this in the data. So you can see that for a given distance a galaxy is away, it's not moving as fast as we might have expected from Hubble's law, which is kind of an odd thought. Therefore, maybe some of our assumptions having to do with Hubble's law are actually not so. For example, one of our assumptions was that all of the galaxies move at a constant velocity since the beginning. In other words, the universe as a whole is expanding at a constant rate. Well, clearly, maybe that's not true. Maybe we have maybe this curve here has to do with some sort of acceleration of the universe. Either it's speeding up or it's slowing down over time. Much like if you're driving your car down the road at a constant speed, you're not accelerating. But if you hit the gas, you accelerate forward, you hit the brake, you accelerate backwards. So one of our questions is going to be, is the universe speeding up over time, or is the universe slowing down over time? Our first thought would be that it probably would make sense for it to be slowing down over time, because the gravity of all the rest of the universe would be pulling on it. So we're going to see if that actually is the case. So let's now look at our graph and read the caption. The caption says, each point on the plot represents a galaxy where a type 1 supernova has been observed. On the y-axis is plotted the recessional velocity of the galaxy, and on the x-axis represents the distance to the galaxy. The errors in the distance and velocity are also shown. The dashed straight line represents Hubble's law with Hubble time of 14 billion years. So now that we understand what we're plotting, which is the distance and the velocity, notice that the locally measured Hubble constant is about 70 kilometers per megaparsec, which is consistent with our last video, which is the slope of the line in the graph above. That's that. Implying that the Hubble time is about 14 billion years. However, the farthest galaxies are clearly below and to the right of this line. This means that they are moving slower than one would have expected from Hubble's law. To investigate these data further, we are going to find the velocity in the center of the data at the following distances: the corresponding Hubble constant, which is the slope of the curve, and its ratio to the local Hubble constant, and this ratio is called the expansion rate. In other words, by definition, things that are close by have an expansion rate of 1. So these distances are 1,000, 2,000, 3,000, and 4,000 megaparsecs. So those are what we are going to measure. Now we will begin at 1,000 megaparsecs, and I'm going to draw a line like that. Now you can see we have our line here that we've drawn through the data right through there. So the approximate corresponding velocity is measured just like we did before by drawing a horizontal line like this. So here we have 50,000 kilometers per second, 100,000. That's about a tenth. So I'm putting it as 60,000 kilometers per second in my table. So here is that line that I just drew, and you can see it a little better now that it's highlighted. So in order to find what the Hubble constant centered around this, we are going to now find the rise and the run and define the slope here. Recall, the slope here was 70 kilometers per second per megaparsec. So the slope here will also be in units of what the units of the vertical axis is, divided by what are the units of the horizontal axis is. Now, we need to discuss a little bit about slopes on graphs. If you are lucky to have a graph with the same type of quantity, with the same units plotted on the x and the y axes, in the same unit, to exactly the same scale, what's referred to as a square graph, whether or not the whole thing looks square, it doesn't matter so long as that's the case, then it's a square graph, then you should be able to just measure the rise and the run and divide them. You likely did that a lot when you took a math class in the past. However, in this case, our velocity is in totally different units than our distance. So all slopes are going to be in units of kilometers per second divided by megaparsecs. The other thing to notice is that this axis here is to a totally different scale than this axis here. If I go from here to here, I've gone, this is 1,000 megaparsecs, and whatever I measure that to be on here, let's see, 1,000 megaparsecs appears to be 20 millimeters, or 2 centimeters. That's completely different than 1,000 kilometers per second, which is probably a little teeny tiny bit down here. So we have to measure the rise and the run in actual units of what the actual axes are in order to find a legitimate slope. That said, how big of a line I drew here to fit it, and how big we pick here or here is arbitrary so long as we pick corresponding points. So, in our particular case, I drew a line here that, as I recall, was about 2.5 centimeters long. So this side here, if I measure it, is 2.123, about 2.25 centimeters. So I'm going to write that down, 2.25 centimeters. And now I'm going to measure the rise, the corresponding rise, which appears to be 1.4 centimeters. Now again, I cannot just say 1.4 divided by 2.25, because this axis represents something real and physical, which is the distance to the galaxies. And this axis represents a different thing that's real and physical, which is the velocity of the galaxies. So I'm going to have to convert this over to the velocity difference and this over to the distance difference in order to find the actual slope of this line on this particular graph. So again, slope is rise over run. our rise is the change in velocity, which I'm going to call delta V, delta for change in, and V for velocity. And run is the change in the distance, which I'm going to call delta R, delta for change in and R for distance. Now, what we're going to do is we're going to measure the scale of each axis, and from that, we can calculate what this is and what this is in units of kilometers per second for this and megaparsecs for this. So let us begin with the vertical scale. This vertical scale ranges from 0 to 300,000 kilometers per second. Remember, that was the speed of light. So if I measure it in the same units as I measured here, which was centimeters, doesn't matter what units so long as you measure this in the same units as this. Had I used millimeters here, I'd have to do this in millimeters. If I had used inches here, I'd have to do this in inches, etc. So I start out, let's see, 0. This is 8.5. So now I know that I have 8.5 centimeters corresponds to 300,000 kilometers per second. So we can write our vertical scale now as equal to what we're interested in divided by what we actually measure. So our vertical scale is equal to 300,000 kilometers per second divided by the corresponding length, which is 8.5 centimeters. So if I divide that out, I get 300,000 divided by 8.5 equals 35294, which is 35,000 kilometers per second per centimeter. Now we'll measure the horizontal scale. 12 centimeters even is 6,000 megaparsecs. So 6,000 megaparsecs divided by 12 centimeters equals 500 megaparsecs per centimeter. So now we know our vertical scale and our horizontal scale. We've now measured our rises and our runs in centimeters, so let's calculate what they are in the units that matter, which for rise is kilometers per second, and for run is megaparsecs. Recall that our rise in centimeters is 1.4 centimeters, which corresponds to 49,000 kilometers per second, because 1.4 centimeters times our scale in kilometers per second per centimeter is this, because as you can see, our centimeters on the page cancel. Notice this kilometer is a real kilometer, and this centimeter is the centimeter on the page. And similarly, we measured the horizontal distance to be 2.25 centimeters, and the horizontal scale to be 500 megaparsecs. And remember, these two were corresponding. Then, when I multiply those together, my centimeters on the page cancel, and I get about 1,000 megaparsecs. Clearly, I wrote too many significant figures here, so I would kind of interpret this as like 1,100, but I'm going to keep an extra couple of digits just until the next calculation. So now, by putting these together, our slope is our rise divided by our run, which is our velocity change divided by the corresponding distance change, which was 49,000 kilometers per second divided by 1,100 megaparsecs, and I get 43.5 kilometers per second per megaparsec. And I see that the Hubble constant as measured around here is 43.5 in these same units, because that's what I got. Notice this is significantly smaller than that. So if I find the ratio of this to the local Hubble constant, I will get this number divided by 70. So I'm going to take what I got, divided by 70, equals 0.62. So I have about 62% of what the Hubble constant is when I measure it close by. Now, there's a caveat to consider when we did this. The main caveat to consider is that the distance that these galaxies are from here is about 1,000 megaparsecs, which is about, if you look up here, about 3.5 billion light years. So it took light, that's what look-back time is, about 3.5 billion years to get from there to here. So imagine that we were looking at the universe as it was 3.5 billion years ago. Well, we actually would not get this same Hubble constant if we're looking then, because the primary thing the Hubble constant actually measures is the age of the universe. The secondary thing it measures, it might have to do with what the universe was like 3.5 billion years ago when the light left there. So we're going to have to disentangle those two things. And so we're going to do that by dividing by the local Hubble constant. The other caveat I want to say is that in order to make this plot, I had to take the data and apply some general relativity to them to get the actual speed that things are moving. And to calculate that in such a way so that this velocity divided by this was the actual Hubble constant. I did that, and you just have to trust me on that. So we're going to now do the same thing at these other distances in megaparsecs. So you can maybe see this green line here that I drew as an approximate slope here. And I'm going to measure this and this for it. So I measured a run of 2.1 centimeters and a rise of 1.2 centimeters. This was our calculation, remember, at 1,000 megaparsecs. Now our calculation at 2,000 will be similar, except this number here will be 1.2 centimeters, and this number here will be 2.1 centimeters. So I'm going to change that. I'm going to erase this, and I'm going to make the same calculations again, except this is 1.2 centimeters, and this is 2.1 centimeters. And then if I take 1.2 times 35300, I get 42360 kilometers per second. And again, I only really know this to a couple of significant figures, maybe two at the most. I'm still going to keep the extra digits on my calculator, and I do this on this calculator by adding it to memory. And now 2.1 centimeters times 500 megaparsecs per centimeter is 1050 megaparsecs. So now I have my numerator here in kilometers per second divided by 1050 megaparsecs equals 40.3. So notice here we have 40.3 kilometers per second per megaparsec, which is a little bit less than we had before, but not by very much. So putting a green highlighter here, you can see that at 100,000 kilometers per second was pretty much smack in the middle we were talking about. So I'm going to write down here 100,000 kilometers per second. And I'm going to put here what we just calculated, which was 40.3 kilometers per second per megaparsec. And then take that number and divide that by the close by value, which was 70, and I get 0.576, or about 0.58. Okay. Notice these do not have units because it's the ratio of something to something else, both in the same unit. So now we will do the same thing here and here, and we will see what we get. Notice something else. You see how the error bars get bigger and bigger as we get further apart? So the farther away the galaxies, the larger the error in the distance. Notice how the error in the velocity is very small no matter where we are. And that's because with modern technology, the way that we find the recessional velocity of galaxies is by measuring a spectrum and using the Doppler effect. And we can do that very precisely. On the other hand, to find the distances to galaxies, we have to assume that something is the same luminosity, whether it's there or nearby. So these errors here are always much bigger because they have to include not just how bright we measure these faraway supernovas to be, but also the fact that they might not be exactly the same. And we're assuming that the farthest away supernovas, if they look the same in other ways that don't depend on distance, are the same. So for the next one, if you look at the yellow line here, I measure 2 centimeters this way, and I actually drew it to be 2 centimeters, and it just came out to be 1 centimeter this way. And this was where the center appeared to be, which if you think of this as 100,000, that's probably like what, 1, 2, 3, 4, 5, 6, 7, 8. So maybe it's 1,450, something like 145,000, 145,000 kilometers per second. Maybe that's about where that is. So at our distance of 3,000 megaparsecs, we had 1 centimeter rise and a 2 centimeter run. So remember, you can't just say the slope is 1/2. And then we have this divided by this times that, divided by that times that, which is this divided by that, which comes out to be about 35.3 kilometers per second per megaparsec, which we then put down here as the Hubble constant, and then we put down here the ratio of this to the Hubble constant now, which is just about 1/2. So the expansion rate here is about 1/2 compared to the 1 as defined here. And for the last one, I measured a rise of 0.8 centimeters and a run of 2.0 centimeters. And notice that since that was 0.8 and this is 1, and it was the same run, It should just be 0.8 times that, and you can double check that. And you have to open parentheses if you divide by two things multiplied together, and then close them. Otherwise, it will multiply this one by everything assigned totally different. So always be thinking about what your answer might be before you type on the calculator. Therefore, if you type wrong, you know that you made a mistake. So now I've filled this whole thing in. So now you can see that as we look further and further away, the ratio of the apparent Hubble constant to what we measure close by is going down. And usually when we have numbers that are a little below 1 that are ratios, we'll often refer to them as a percentage. So this might be 62%, 58%, 50%, and 40%. So the bottom line is, the further away we're observing, even though everything is going faster, it's not going as fast as we might have expected from a uniform expansion rate. Now, for those of you who've taken high school physics, for example, this might seem confusing, because when curves look like this in physics, when it's a velocity versus a time curve, and they look kind of like this, it means something is slowing down. So we often have a memory of graphs shaped like this and things decelerating, even if it's a totally different thing being plotted. So it's really important that you read the graphs carefully so you understand what it is that was plotted. In our case here, it's velocity and distance of galaxies that we look at. Not an individual galaxy, it's not like something moving along. And up here we have the corresponding look back time, which is how long ago the light left that galaxy. So if we want to convert this to some sort of rate versus time, we're going to have to think about that a little more to figure out some history of the universe. For example, what's the best measure of the rate that the universe is expanding? Well, maybe it's the expansion rate we just calculated. So what do we need to do? If we want to plot on this, on the horizontal axis, let's say time as it moves along, and on the vertical axis how fast the universe is expanding, maybe we want to plot this as a function of time. So the next part asks you to do exactly that. So when we look at things far away, we see them as they were when the light left. This light travel time is known as look-back time and is plotted on the top axis. Copy into the table below the look-back time and the expansion rate in chronological order from left to right. Now, chronological order means the bigger the look-back time, the longer time ago. So if we're going to plot time this way, time is increasing from a long time ago to now. So think of it like years BC, for example. Imagine that this were 13 billion years BC, and this were about 10 billion years BC, and so on down. So remember, the look-back time is just a function of the distance. It's just how long it took light to get from there to here. So if the look-back time, let's say at 1,000 megaparsecs, the look-back time was about there. Okay? It was about 3.2 something, maybe 3.25 billion years ago is when the light left. Another way to look at that is that's about, the distance corresponds to about 3.25 billion light years. So that's what we filled in here. And then this expansion rate at 4,000 was 40%. So we're just going to write it as percentage. And then at 3,000 it was 50%. And at 2,000 it was 58%. And at 1,000 it was 62%, which we can see right here. So now that we have time increasing this way from essentially negative 13 billion years to now, and the expansion rate corresponding to each of those times, we can then make a plot having to do with making the expansion rate as a function of look-back time. So for example, in the first case we have 13 billion years, so that's about here, and we have 40%, that's here, so our point is something about there. Okay, so 9.9 is just this side of 8, because it's just past 10, because remember it's BC, that's for all practical purposes, or BP for before present. And then that's 50%, so let's put that there. And then 6.6 at 58%, and 3.3 at 60%, and of course 0 at 100%. So it looks to me like the universe is moving faster over time. Okay, so it used to be going less fast than it is now, and now it's here, and so it's got some sort of increase over time. So now we just plotted our expansion rate over here as a function of time, so that this is the look back time. Therefore time is increasing this way. So that's 14 billion years before the present, 12 billion years before the present, and so on. And you can see this is pretty much increasing over time. If I find the slope of this here, you can find, let's see, if we point here, that's 6 billion years, and this is 13, and this rise is 60% minus 40%, which is 20% or 0.2. So this slope down here should be about 0.2 divided by, what do we say, 6 minus 13, or 13 minus 6, which is 7, and I get 0.03, and those are in units of, we already put this out of percentage, so it's in units of per billion years, or 2.8% per billion years is another way to look at it. So this here is 0.03 per billion years, or 3% per billion years. And that's the slope of the expansion rate. That, we can imagine, is the acceleration of the universe. Now you can see our more recent values look like they should be a little steeper. So if we found the slope somewhere around here, we might find, who knows, something like this. And that's about, let's see, this is about 70% is here. Maybe by the time we're here, it's almost 80, 79 to 99. So call it 99 minus 79, about 20%. Again, 0.2 per 2 billion years, or about 0.1 per billion years, or about 10% per billion years. So we can see that the universe is expanding, is accelerating in a positive direction, something between 3% and 10% per billion years. Now, what's interesting is that astronomers had no idea that the universe would actually be expanding. So now we just plotted our expansion rate over here as a function of time, so that this is the look back time. Therefore, time is increasing this way. So that's 14 billion years before the present, 12 billion years before the present, and so on. And you can see this is pretty much increasing over time. If I find the slope of this here, you can find, let's see, if we point here, that's 6 billion years, and this is 13, and this rise is 60% minus 40%, which is 20%, or 0.2. So this slope down here should be about 0.2 divided by, what do we say, 6 minus 13, or 13 minus 6, which is 7, and I get 0.03, and those are in units of, we already put this out of percentage, so it's in units of per billion years, or 2.8% per billion years is another way to look at it. So this here is 0.03 per billion years, or 3% per billion years. And that's the slope of the expansion rate. That, we can imagine, is the acceleration of the universe. Now you can see our more recent values look like they should be a little steeper. So if we found the slope somewhere around here, we might find, who knows, something like this. And that's about, let's see, this is about 70% is here. Maybe by the time we're here, it's almost 80, 79 to 99. So call it 99 minus 79, about 20%. Again, 0.2 per 2 billion years, or about 0.1 per billion years, or about 10% per billion years. Now, astronomers prior to around 2000 basically had very little idea that the universe would actually be accelerating in a positive way. We all figured, well, the universe probably is going to be decelerating because gravity would pull on it. So nobody imagined that this would actually be going up. Everybody imagined that it would be going down. So now the question is, why is it going up? Well, that's a big question for another time. But what's more interesting is that it's going up in the first place. So remember, because that was true, astronomers just figured that the slope of this line would be in the downward direction. So they defined what's called the deceleration parameter, which was Q, which was just a normalized version of this. Now notice, this is per billion years. Now notice, this is per billion years. So this slope we just calculated is per time. And remember, the Hubble time is in billions of years. So if we take each of these and multiply it by the Hubble time, we should get a normalized slope. And so the normalized slope, which would be one that we might say, oh, it doesn't have any units because we normalize it to now. So you can see that the normalized slope is about 0.4, maybe a little more, maybe 0.5, 0.6, something like that, if you include our current time here, our current point for now. So that would be thought of as the acceleration parameter, but like we said, astronomers had no idea that the universe was actually speeding up, so they defined a deceleration parameter that was just the negative of that. And so that's often referred to as Q. Best values of Q given these data is on the order of -0.5 to -0.6. But I like to think about it as the acceleration parameter is negative Q, and it's about 0.5. So let's move on to letter C. We now know that the universe has been speeding up since the beginning, and we know that if we assume that the universe was expanding at a constant rate since the beginning, then it would be about 14 billion years old. If the universe were accelerating not at all, then it would be traveling at it would have been expanding at a constant rate since the beginning. And then we would have expected this graph to look like this. What that means is that if this graph were flat, then we would have an age of the Hubble time. But the universe has been speeding up over time. So the expansion rate early on must have been less than the expansion rate now. Therefore, it wasn't expanding as fast before, and now it's expanding faster. So the concept of the universe is accelerating and getting faster over time in and of itself should imply a longer age of the universe. And in fact, if you look back here, you can see that some of these galaxies, while they might be consistent with being 14 billion light years away, some of them appear to be even more further away. So you can see that if you drew this kind of like this, who knows, it might be significantly older. There is a caveat to this, a big one, and that is that the actual age of the universe depends a lot on what happens in here, meaning what was it like a long time ago and how did these curves work? For example, what if this curve was a little more like that? Or what if some of these points here were basically scatter from the trend and, maybe it's more like that. So the real question then becomes not how much older it is, but that it is older according to these data. Now there's another caveat too, which is that the way that I calculated these distances and the way that I picked the velocities is somewhat subtle at very far distances. Sometimes these distances have to do with what's called the luminosity distance, and some of them have to do with other parameters that can change as you get very far, as you're looking way back in time, because Einstein's theory of gravity, general relativity, becomes important. And I made a number of simplifying assumptions when I made this graph. And I made sure that my simplifying assumptions were such that Hubble's law would be a straight line on the graph. So, putting all those together, the age of the universe may or may not be the Hubble time, and depending on which model you pick, it's kind of around the Hubble time. And so there's details when you're very far away, but if you just look at these data, you probably think it was significantly older. And that's not even to mention that there are a number of different theories that would suggest that the universe may be expanded very quickly early on and then slowed down, in which case the expansion rate might have been something like this. So who knows? But those aren't revealed in the data that we're looking at. And one thing to keep in mind about astronomy is that astronomy is an observational science. And observers observe things and we can interpret them. And how sophisticated an interpretation depends on how well we know the physical theories involved. And clearly, we don't know this one very well. And so it'll be very interesting to figure out the actual age of the universe over time, even as the Hubble time remains 14 billion years. So I filled in here, given the universe used to be expanding at a slower rate, it would have taken longer to reach its current size. So now we're going to say, find the slope here, multiply it by 14 billion years, and say 0.03 times 14 equals 0.4. And now we will do the same thing with the slope that we figured here, the much bigger slope toward us, which was about 0.1 per billion years. So we're going to say 0.1 times 14 is 1.4. Now, as mentioned at the very beginning, the data that we used for this activity was related to the Nobel Prize in Physics in 2011. In 2011, the Nobel Prize in Physics was given to the astrophysicist Saul Perlmutter and also to Brian Schmidt and Adam Rees for the discovery of the accelerating expansion of the universe through observations of distant supernovae. So according to the press release, it says, written in the stars. Some say the world will end in fire, some say in ice. What will be the final destiny of the universe? Probably will end in ice, if we are to believe this year's Nobel laureates in physics. They have studied several dozen exploding stars called supernovae and discovered that the universe is expanding at an ever-accelerating rate. The discovery came as a complete surprise even to the laureates themselves. And it continues on. In 1998, cosmology was shaken at its foundations as two research teams presented their findings. Headed by Saul Perlmutter, one of the teams had set to work in 1988. Brian Schmidt headed another team, launched at the end of 1994, where Adam Rees was to play a crucial role. The research teams raced to map the universe by locating the most distant supernovae. More sophisticated telescopes on the ground and in space, as well as more powerful computers and new digital imaging sensors, CCD, Nobel Prize in Physics in 2009, opened the possibility in the 1990s to add more pieces to the cosmological puzzle. The teams used a particular kind of supernova called a Type 1a supernova. It is an explosion of an old compact star that is as heavy as the Sun but as small as the Earth. A single such supernova can emit as much light as a whole galaxy. All in all, the two research teams found over 50 distant supernovae whose light was weaker than expected. This was a sign that the expansion of the universe was accelerating. The potential pitfalls have been numerous, and the scientists found reassurance in the fact that both groups have reached the same astonishing conclusion. For almost a century, the universe has been known to be expanding as a consequence of the Big Bang about 14 billion years ago. However, the discovery that this expansion is accelerating is astounding. If the expansion will continue to speed up, the universe will end in ice. The acceleration is thought to be driven by dark energy, but what that dark energy is remains an enigma, perhaps the greatest in physics today. What is known is that dark energy constitutes about 3/4 of the universe. Therefore, the findings of the 2011 Nobel laureates in physics have helped to unveil a universe that, to a large extent, is unknown to science, and everything is possible again. So, thank you for listening to this video about the acceleration of the universe.